Okay. So next Wednesday, 27th of May, we will take quiz two. Okay. And it will cover lecture 6 to 10. Okay. So lecture 6 is transformer, and after that is the range of the quiz two. Okay. And there will be no calculation this time. Okay. Okay. So this is actually the last lecture. Okay. So we will see how in previous lecture, we have learned the LLMs, the language models, okay, large scale language models, okay, several, and especially the open source ones like the Llama and Quen and DeepSeek, okay. And also, we also see this belief, one of the initial VLMs, vision language models. And today, we will see more advanced feature for the VLMs. And actually, the lecture slide has been slightly updated. So I already updated it in the Blackboard. Okay. And another announcement is assignment 2 is noticed. Okay. So its deadline is by, as far as remember, 21st of the June. Okay. So please start that. Okay. And this is the Flamingo, which is the initial VLMs, Vision Language Models, which input both the images and also the text. Okay, so they are inputting both images and text. Okay, and their outputs are text. Okay, this is the early stage VLMs. Okay. And mostly they are doing few shot learning. Okay, so in the input prompt, they are giving some many information about the images, and they are wanting to generate some text output that describes the last images. Okay, that is what Flamingo does. And Flamingo was initially intended to achieve this fusion learning. Okay, and similarly here, for first images, two images, they are giving some desired output and wanting to estimate the description for the last one, similarly to the first two images. So in this sense, they are doing two-shot learning. Okay. And similarly here, they are giving some output for the first two images and wanting to enforce Flamingo to generate the last image descriptions. Okay. And here as well, they are giving some video and I mean, enforce some text output as well. And they are also doing some multi-turn text generation. This is the first early VLMs. Okay. And they are covering 16 tasks, okay, for doing some VQA, visual question answering. So seeing the images, they are wanting to answer uh, the description related to the images in the form of the text output, okay. And the Flamingo, they are saying that compared to the other zero shot or few shot state of the art, they are producing better capability for this zero shot and few shot text generation. Okay? And also they are publicizing three types of models depending on the parameters. And they are also observing that when their parameters are becoming larger, then their performance is becoming better. Okay, observing the similar trend in the LLMs. Okay, and this is the architecture of the Flamingo. This is the clip-like vision encoder and text encoder. They are first trained both vision encoder and text encoders similar to the clip. And in this work, they are additionally trained these pink blocks. Okay, so additional perceivable resampler, which maps the initial vision encoder's responses to the LLMs. Okay, they are further mapping, transforming the vision features to input it to the LLMs. That is done by this perceivable resampler. And also they are having another layers before uh, the language model blocks. Okay, and eventually what they are wanting to achieve is, given this first images description, they are wanting to generate the second images descriptions. Okay, and what they are basically does is they are having some interleaved visual and text data, and for the text part, they are inputting it to here. And also for the image part, they are first extracting visual features via the vision encoder and transform it via this perceivable resampler and feed it to this module. And then by mixing the vision feature and language features, they are eventually generate the output, the text output. That is what Flamingo does. And this part, they are what they are. So that part is magnified here. And what they do is they are first, this part, they are mixing the vision input and language input using the cross attention mechanism. So key and values are coming from the vision signal and queries are coming from the language signal. And by doing that, they are somehow mixing the visual language signals, okay? And then apply another language modules, okay? And then by repeatedly constitute this architecture, they are somehow mixing the visual language signals and then eventually produce the text description, okay? That is the Flamingo. And they are insisting that compared to other state-of-the-art zero-shot fusion learning method that combine visual and language signals, the Flamingo, they are producing better zero-shot or few-shot accuracies. Okay, that is what Flamingo does. And actually, Flamingo, that is doing very similar thing to the Blip, but we can regard this Blip and Flamingo as the concurrent work, okay? And additionally, this Flamingo was developed by DeepMind, okay? And the other early stage VLMs are Blip version 2, okay? Published in ICML 2023, okay? And believe that have two stages for training. Okay, the first part they are doing the pre-training. Okay, they are training the vision language representation learning first, and then they use this Q former, which is the query transformer, to apply it to the LLMs and eventually generate some text descriptions for this vision language input. Okay, that is Blip version 2. They are first train this Q former, which is the query transformer, and then use it I mean, to feed it to the LLMs, existing LLMs, to generate the text outputs. Okay, that is the Blip version 2. And you can also see here in the Blip, they are freezing the LLMs. They are not actually training the LLMs, but only train this Q former, okay, which provides some queries to the subsequent LLMs. And that actually limit the capability of this Blip version 2. And this is explaining more about the first stage training of the Belief version 2, okay, the Q-former training, they are uh, explaining in detail, okay. So this is the the vision signal part, okay. They are using the freezed image encoder to extract some initial features from the images. And in Q-former, they are actually having two transformers. The left one is the vision transformer. The right one is the text transformer. Okay. And they are similar to Blip version 1. They are applying three loss functions: the image text matching loss, image text contrastive learning loss, and image grounded text generation loss. Okay. This is similar to Blip version 1. And the first one, image text matching, they are binary classifier. If text and images are matched, then they are producing one, the binary value one. Otherwise, they are producing zero. And image text contrastive learning, that's similar to CLIP, and they are make the image feature and text features similar when they are matched, or otherwise they are making their distance larger. That is the contrastive learning rules. And the last one, image grounded text generation rules, that is generating the text from the queries. Okay. And here, how to say, this vision part is, producing some output given these queries coming from the image encoder and text transformers. They are directly input the text signals to output to generate the output. And also in here, they are using three different masking policy, because for this image text matching part, sorry, uh, this is also very simple things. For image text matching, this query is visual signal and text is the T is the denotes the text signal. And the I mean these two are showing the input space, and this is showing the output space. Okay. So when when doing the matching between text and visual signals, for calculating this image text matching part, they are seeing all the queries. They are seeing this is the T query, and this is the these queries are denoted as Q, and the queries here for text input text is denoted as T. So when calculating this image text matching rules, all the queries are seen together. But this is denoting, for example, this is denoting that when, how to say, calculating the second rules, image text contrastive learning rules, uh, when generating output for this vision part, we have to see only vision queries. And also, when calculating the output for this text transformer, we have to see only this input text queries. Okay, so that is actually denoted here. Okay, so when outputting text, only text part are attended together. And when outputting the query part, only the vision query, their inputs are attended together. And uh, when outputting the queries, the text queries are masked, and they are not used for the vision transformer. Okay, so that kind of things are encoded in these masks. And also when calculating the last loss, this is actually the loss for generating real sentences. Okay, and when given only vision transformer, they do not have to see the text input. Okay, so for generating queries, for generating text, uh, they are not Vision queries, Vision transformers. They are not intended to use the text input, and also for even for the text transformer. Actually, the text outputs are sequence data, and when generating the first text output, they are only seeing text queries, which is reserved for earlier text word. Okay, and when generating the last text word, they can eventually see all the text tokens. But for earlier text, how to say the earlier part of the word generation task, they are using only earlier text tokens. Okay, combined with some of the visual tokens. Okay, that kind of thing is considered here. Okay, so for three different tasks, they are using three different masking policy. And anyways, this Q former is trained to align the vision and text encoder, text transformers, and they are eventually generating the text output considering both visual language signals. That is the Q former. Okay. So the first stage of the Blip version 2 is pre-training this Q-former. And then the second stage of the Blip version 2 is using this Q-former. They are actually provide two use cases. The first one is the use cases for having decoder only LLMs like the OPT. Okay. And another use case is when language models, they are having both encoder and decoders. Okay. They are providing two use cases. And using the Q-former that we have trained in the first stage, they are inputting input images into the freeze input image encoder, and using the Q-former, they can generate some initial text, output text. Okay, and then they are feeding this output text by via this fluid layer. Okay, and this becomes another input to the LLM decoders when only the decoder of LLMs are available. And when there are both encoder and decoders are available for the LLMs, they are doing the same. They are first generating some text output via QFormer and apply fully connected layer on that and use this as the LLM encoder's input. Okay, and somehow they are mixing the how to say they are interpreting this as the how to say the information about the vision, okay, vision signals, and then generate the final output text. Okay, and also when LLM encoders are available, they can also encode another text signals. Okay, so they are especially can mix the first part of the text and then mix it with the vision signals and then generate some new text output. Okay, so this is the use cases when LLMs they have both encoder and decoder, and when LLMs have only decoder, uh, they can only generate text from the vision signals, but when encoders are additionally available, they can also feed more text to the LLMs. And the thing we have to observe, notice here is the LLMs are fixed, they are freeze. So in Blip, they are not explicitly train the LLMs, but train only the Q-former, which is the transformer that manipulate the queries to the LLMs. Okay, that's the Blip. So Blip version 2, they are surpassing the Blip and Flamingo, which is the previous version of the VLMs. Okay, in multiple tasks, VQA and image captioning and image text retrieval tasks, they are surpassing the previous VLMs. And instruct VLM, instruct belief, that is also advanced version of the belief. Okay, and their architecture is also very simple. Okay, so for example, they are inputting input images and also some instructions from the user. And they are reusing the Q-former, which was trained in Blip version 2. But here, what they additionally, the input is some instruction from the users. And uh, they actually, how to say, improve these instruction sets as well as this vision feature, okay, and eventually feed that into the LLM and produce the final output text from the LLMs, okay. But you have to notice that here in the instruct belief, the LLMs are still not fine-tuned, okay, but they are only improving the prompt queries, which will be the input to the LLMs. Okay, that is actually the characteristic of this belief, and also that is actually the limitation of this belief. Okay. So instruct will believe they are additionally can now input the instructions from the users, but they are not fine-tuning the LLMs, but how to say they only generate some queries, okay, to which is the input to the LLMs, okay, and they achieve they are slightly improve the version the performance for these tasks, and they train this instruct belief using many VQA data sets. And compared to the Flamingo Belief version 2, the early stage VLMs, this instruct belief is improving the accuracy in the zero-shot manner in multiple tasks. And without this instruction-aware visual feature, uh, I mean, they are doing some ablation study on this module. Their idea is quite simple, but they are proving that with this instruction-aware visual feature, they can actually improve the overall performance a lot. Okay, so Instruct Believe is actually performing better than Believe version 2, thanks to this instruction-aware visual feature. Okay, so in Q-format, now additionally input the instructions, and then their features are, I mean, role as the soft prompt, okay? So which is the, I mean, advanced queries, which is the input to the LLMs. That is the instruct prompt. And also, there are another VLMs that extend the QN to the to have the multiple multimodal input. Okay, that is the QM VL. Okay, and also they are also providing the multilingual input, their capability, and QN that is providing three-stage training method for achieving this. Okay, first part, they are freezing the LLM part. Okay, but training only the vision encoders. And in the second stage, they are explicitly training both the LLMs and also the vision encoder. And at stage 3, they are fine-tuning these LLMs for specific tasks. That is the three stages in QNVL. And actually, instruct belief is more like having only stage 1. They are only training the vision encoders. But QMVL, they are explicitly having the training stage that both training the LLM and vision encoder, and eventually fine-tuning that for the specific tasks. That is the QMVL. And by that, they are providing better capability compared to the Instruct Blip and Blip 2 and Flamingos, okay, in multiple VQA tasks. And also, this is the Lava, which is the extension of the Llama for the vision language tasks. Okay, they are using the Llama and extend it to input both image and text, okay, and then generate the text output. And Lava is also having similar ideas. So this is the language models, which is the Vicuna, which is the fine-tuned version of the Llama. Okay? And they are actually inputting two types of input. One is the language signal. So we are projecting the language inputs into some query. And then from the images, using vision encoder, which is the Clips visual encoder, we are projecting it to the vision prompt, okay? And then input both queries as the input to the language models and output the text output, okay? This is the Lava, their architectures. So this idea of projecting the image feature into some query, which is the input to the LLMs, are quite similar to that of the instruct blip and QN. But another difference here, maybe compared to the instruct blip, is Lava is also fine-tuning these language models as well. But instruct blip, they are not fine-tuned or these language models. That is actually big difference. Lava is also trained to have the multi-turn conversational data set. So using these visual images and some instruct text, they are producing actually the text output. And actually that was done uh, actually additionally, how to say, inputting when calculating the answers in the answers in the I's conversation, they have to consider the answers that happened before that I's conversation as well, and all the instruction before the I's time, and also the images. Okay, they are actually the multimodal distribution of, by multiplying all the probability for previous uh, chat histories. Okay, and actually Lava, they are also trained via two stages. At the first stage, they are training only uh, how to say, the visual encoder. Okay. Mm, trainable parameters only. Okay, so they are using this equation three, that is this equation, to find the answer for that I's chat turn. And in the first stage, they are training only the projection metrics. Okay, so this layer, they are only training. So how to convert this image feature to the prompt of this vision, the language models, they are training only that part in the first stage. Okay, and then in the second stage, they are training both LLMs and projection layers. So their parameters are now W and pi. And pi is parameter for the language model, and W is the projection layers. Okay. Stage one, they are training only the projection layer, but in the second layer, they are explicitly training both LLMs and projection layers. That is the Lava. And by doing that, they can provide better capability compared to the previous Flamingo or Blip version 2. Okay. Okay. And even compared to the GPT-4, uh, but this is only the text version. Okay. And they are saying their performance is better than GPT-4. Okay. And also compared to the previous one, they can be better. And this is the simple ensemble between the GPT-4 and Lava, their output combination. And this paper, initial Lava, is insisting that their output is complementary to the GPT-4. And when combining their output, they can produce better accuracy. Okay. And Lava version 1.5, that's the advanced version of the Lava. Um, Actually, they slightly improved the initial lava. So here you can see belief is represent their performance to multiple tasks represented here. And this is the instruct belief. And this is the QNVL, their performance. And this is the performance for Lava 1.5. Okay. Um, they are using less number of samples, but they are producing better performance compared to the other alternatives. Okay. Okay. And their how to say, architectures are quite similar to Lava version 1. So they are basically using the vision encoder and also the projection layer, make the prompt, vision prompt. And also they are mapping the language signals to the queries again and using the Vicuna, which is the Llama, extended version of Llama, and produce the text output. Okay? And one of the things that this paper is pointing out is previous instruct belief because have some limitations. First thing is their LLMs are not fine-tuned, so their performance is limited. And second is their how to say, visual prompt is sometimes ambiguous. Uh, I mean, most time they are how to say, enforcing some short word for the questions. Okay, so they are here in Lava 1.5. They are how to say, explicitly change the prompt to generate only short word for some of the questions. Okay. So instructably, even for this type of instruction, they are not providing long, reasoning words, but instead provide only very short answers. So one of the reason is their training prompt is sometimes ambiguous. So in Lava version 1.5, they are, modifying this type of data prompt. Okay. And also, Lava is also extending their vision encoders to encode the high resolution images. Okay. So initially, the VIT was fed to these all of the patches extracted from the images. But in the Lava 1.5, they are applying several independent VIT for these regions. Okay, uh, to how to say, to properly encode high resolution images. Okay. But instead, they are having additional paths by downsampling the original image and encode that like this. Okay, so this part, the whole images are encoded by just one VIT. So this part, they are providing some global context of the large scale images, but each local regions are encoded independently by separate VITs. Okay, so and by feeding both local independently encoded features and also the global features to the LLMs, they can provide better accuracy. That's the another extension. made in this 1.5 version. So compared to the instruct blip, they are providing more data sets. The blue cells are for the data contribution. They are providing more data, and the performance is by increasing the number of data, their performance is becoming better. And also here in the model side, uh, they are scaling up scale up the resolutions and also uh, provide some of the improvement and thereby achieves better performance compared to the original lavas. Okay. And even compared to the GPT-4, for some tricky examples, the lava is properly providing the result. Okay. So lava version 1.5, they are open sourced VLMs. They are producing a better result compared to the GPT-4. And this is also the comparison to other alternatives, the open source algorithms. And the Lava, they are saying their accuracy is better than others. Okay. And this is the last part. Okay. So nowadays, so far we learned the VLMs whose output, their types are text rather than uh, the physical world signals. But nowadays, we are actually extending the VLMs, the vision language models, to generate some actual physical signals. Okay, that we call that as the vision language action models, VLA. Okay, so this is one such models. Uh, whose model name is OpenVLA. So they are also using the VLM models, but extend their output to produce some robot control policy. So their output is some, how to say, the parameters that can control the actual robot, their arms. Okay. So the vision signals, they are using VLM. So we can input both vision signals and some of the instructions from the users in the form of the text. And then, for example, here, to grasp some object here, how to control this robot is estimated from these VLA models. That's the VLA. And this is the detailed, how to say, pipeline for that. So this is the input image, and this is the instruction given from the user. So put eggplant in bowl. So for doing that, they can also use two types of vision encoder, Dino version 2 and Siglip, okay? And then use this projector to map it to the vision queries. And also these instructions are mapped to these text queries and using the VLMs, using the LLMs, they are producing some robotic controlling policies. And this is some parameters that can control these robots, actual robots. Okay, that is the initial VLS. And now we are also improving these VLS in multiple aspects. Okay. So this is actually the end of today's lecture, and we have so far seen some LLMs, recent LLMs and VLMs, and also the extension for physical AI, which is the VLA. Okay, so and actually this is the last lecture. Okay, and we will take the quiz 2 in next Wednesday, and next uh, Monday, we will also do some final presentation, okay, for the final term project. Okay. So let's finish here for today and see you next Wednesday for quiz 2. Okay. Thanks.